It is my great pleasure to have Dr. soon to be Ryan Schmedding and Dr. Ryan not yet. Missed almost. So Ryan right now is a PhD candidate in the aerosols and clouds and climate research group of Professor Andreas Zuend at McGill University. And his research is focused on the aerosol cloud interactions, surface and interfacial properties of aerosol particles, and size-dependent properties of atmospheric aerosols using the state-of-art thermodynamic mixing models and machine learning techniques. So Ryan actually got his Bachelor of Science and master degrees from University of Carolina, North Carolina. So also he's an air quality fellow at the United States Embassy in Bishkek, Kyrgyzstan, where he serves as a scientific liaison for diplomatic staff on issues surrounding air quality and climate change in Central Asia. She's also passionate about scientific policy and communication. So let's welcome Ryan.
Thanks for the introduction. It's exciting to be an invited speaker at one of these. So this is my first time ever giving a presentation at another university. So I've done this at my own university, but never finally progressed in my career to this point. So yeah, the title of my talk is Just Scratching the Surface, Exploring the Importance of Aerosol Interfacial Properties. I'm gonna move this down. Yeah, there. Okay. First, I'd like to thank my supervisor, Professor Andreas Zuend, as well as the 3 other grad students that I've been working with. And then my funders, so the Fonds de Recherche de Québec, Environment Canada, and MyTax, without whom none of this research would be possible. Brief outline of what I'm going to talk about today. So I'll go over some background and introduction, as well as the modeling framework that we use in our group. Then I'll talk about the surface tension of aerosol particles and cloud droplets. Then we'll move on to interfacial tension and phase separation in aerosol particles and cloud droplets. And then lastly, I'm going to talk a little bit about the surface tensions of individual atmospherically relevant compounds. So let's start with part 1. So this is a massive department. It's way bigger than our Department of Atmospheric and Oceanic Sciences. So just a little bit on the importance of aerosols. So poor air quality is a major cause of death globally. It's the leading environmental risk factor for premature mortality. We can see that there's quite a bit of spatial heterogeneity in terms of exposure to poor air quality. So places like East Asia and India are quite famous for having bad air pollution, as well as parts of Northern Africa and the Middle East, former Soviet republics, Kyrgyzstan over here, where I serve as an air quality fellow, and the former Yugoslavian countries as well. I'd also note that there are like wealthier countries that have issues with poor air quality. You can see Germany here also has a decent amount of deaths attributable to poor air pollution. As you may have noticed, my funding comes from the Canadian government, so I have to smugly point out that Canada is doing slightly better than the United States in terms of exposure to air pollution. But that's not to say that it's not a problem in Canada either. Lest we forget, this is a photo a friend of mine who lives in Manhattan took last summer. If anyone has seen Blade Runner 2049, you know, the scene where they go to like Las Vegas and it's like this nuclear wasteland. We had that in real life with air pollution last year. So Montreal, where I live, we had the worst air quality in the world. And then around the same time, New York City had their worst ever air quality, which was actually National Clean Air Day up in Canada. And ironically, on that day, the air quality was actually quite good in Montreal. So funny how the atmosphere works, right? So talking about the individual contributors to poor air quality, one of the primary ones is atmospheric aerosols. So these are like tiny particles suspended in the atmosphere, and they have a range of sizes. So different sized particles form through different mechanisms, right? You have your coarse mode particles, which usually form through like mechanical things, so like a dust storm or anything like that. And then you have your nucleation, egg kit, and accumulation mode, I won't go into the mechanisms by which these form, but basically these are, in terms of the number of particles, like the dominant fraction, and they're also the smallest. As particles age, they undergo chemical transformation, and they're eventually processed by the atmosphere and removed possibly through precipitation. So freshly emitted particles, especially if they contain organic compounds, these organic compounds tend to have very low oxygen to carbon ratios. So they tend to be very nonpolar, and they don't like to mix with water. So it's around lunchtime. If anyone has had a salad or is having a salad for lunch, if you think about like the oil and vinegar in your salad dressing, they don't mix, right? You have like your oil on top and your vinegar below it. The same thing can happen in an atmospheric aerosol particle. So you have your organic rich phase. So your green here is your organic rich phase, and your blue is your aqueous phase and your electrolytes. So basically what happens is these two phases don't mix, and you end up with an enrichment of electrolytes in the aqueous phase, and an enrichment of the organics in the organic phase. Then the actual like three-dimensional structure of these particles can change too, right? So they can be spherical, which makes describing them mathematically quite easy because physicists love spheres. But they also can be non-spherical, right? So you could have what's called a partially engulfed particle here. So that's like when you have some sort of lens of organic material on the exterior of an aqueous droplet, and that can either be like a tiny occlusion or like an almost complete coverage. Those tend to be much harder to describe mathematically because they're not spherical. Now, as these particles age in the atmosphere, they undergo photochemistry, right? So they will gradually get a larger and larger oxygen to carbon ratio. And what this does is it encourages those organics to mix with the inorganic species until eventually your particle will revert to a single well-mixed phase where all of your organics are homogeneously mixed within it. And if the humidity continues to grow, then that pollution particle will be removed by rain. So it's really important to understand how aerosol particles can end up as precipitation in terms of the interactions between poor air quality and weather. So how do we actually measure these kinds of, or sorry, not measure, model these kinds of behavior? So when the water content of a particle is very low, all of your species tend to be very, very highly concentrated. And what that means is you get what's called non-ideal mixing. So basically, if you think of a particle in dilute conditions, we can say that that mixes ideally because most of your interactions will be between individual solute molecules and water. So if you think about this little figure here on the bottom left, you have your sodium, which is this red square, your benzene, which is the green hexagon, and I think the chloride is probably covered by this gray thing here. But you can see they're basically completely surrounded by water, right? So they're only really interacting with water like a molecule to molecule interaction basis. However, at like a lower relative humidity, you would have a much more concentrated solution. And now your interactions between benzene and sodium and chloride, those start to matter in terms of the total energy of mixing of the particle. So we can't neglect these anymore. So in order to fully understand the range of conditions that a particle would experience, we need to be able to model both the dilute systems and the concentrated systems. So we use that with a model called IMFAC. This is, I think, the slide with the most math, and it's only 4 equations. So I did the best that I could. So if we think of the total Gibbs energy of the particle, there's various conjugate pairs of variables, right? Temperature and entropy, pressure and volume. There's also one called chemical potential, which is basically the energy per molecule in a system. So your chemical potential is this term mu here, and it's multiplied by your number of molecules, J. And then mu is actually 2 components, a reference state chemical potential and a chemical activity. So a common assumption is that these mu naught terms are all the same, which actually greatly simplifies things. And then you have your chemical activity here, which is your concentration times an activity coefficient. What that gives you is basically your effective concentration of species. So under equilibrium condition, all of your effective concentrations have to be equal to one another. So your concentration times activity coefficient in phase alpha, beta, and any other phase must be equivalent. So what that means is that in the gas phase, those activities have to be equivalent to in the particle phase. And then in the particle phase, you could have at the moment up to 2 liquid phases, alpha and beta. So this is your aqueous phase and this is your organic phase, because aqueous phases are always blue and organic phases are always green. I think like the community's collective design decision at some point was to make those 2 colors. So as long as your activities are equivalent between these 2 phases, that will feed back on the particle phase composition, which also feeds back on the gas particle partitioning of different species. So all of these things are kind of connected. How do we actually get the activity coefficient? So we use this model called IMFAC, which is the aerosol inorganic organic mixtures functional groups activity coefficients model, which is a mouthful. But basically what we do is we use a solution of groups approach. So in this case, it's ferulic acid, water, and sodium chloride. This is just like kind of an example system here. But we break each species up into its constituent functional groups. And then we use a solution of groups here. So like your hydroxyl, ether, et cetera. They don't necessarily know that they're connected to this larger molecule. And then we take the concentrations of the individual species and we can get activity coefficients out here. So how that works with relation to the partitioning between these different phases is that basically we use a system of equation solvers to find this equilibrium concentration point. And then at each step, we are generating these activity coefficients. And then eventually at equilibrium, all the activities are equal, and that's our particles morphology. So now we're going to change topics a little bit and talk about surface tensions of particles and droplets. So when we talk about sort of classical thermodynamics, surfaces are often treated as a 2-dimensional dividing plane. It's defined out of mathematical convenience where like the excess concentration of different species are 0, which is kind of a hard thing to actually measure in terms of like where that would exist on a droplet. So instead, we use a 3-dimensional interfacial region, because if you think about any molecules that are adsorbed onto the surface of a solution or partitioning in from the bulk, those have some sort of like finite volume, so we have to account for that. So we use this 3-dimensional interfacial region with depth delta here. So what this is basically a case of forced liquid-liquid phase separation. So when we solve for liquid-liquid phase separation in a bulk solution, you could have one phase be like infinitely small, and that's a valid solution, or you could have 2 phases with the exact same composition, and that's a valid solution. But the interesting thing about a surface is that it always exists. Even if you were to like take your aerosol and like put it in a glass box where it's touching the glass on all 4 sides, you'd still have some kind of surface at the glass solution interface. It's also volume constrained. So in the liquid-liquid phase separation algorithm, again, one of these volumes could be infinitely small, and maybe that satisfies the mathematical conditions. But in this case, it has to be this depth delta, so like a spherical shell of depth delta. So the other interesting thing is that aerosols are finite volume, right? So as I mentioned before, all these aerosol particles are really, really small, which means that if you start moving things back and forth from the surface in the bulk, you end up changing the concentration of things in the bulk if they move to the surface, and changing, you can move things to the surface and deplete them out of the bulk, or you can move things from the surface and enrich them in the bulk. So when we talk about compounds like surfactants, those would be species that are moving preferentially to the surface and depleting out of the bulk. And when we talk about like electrolytes, those would really prefer to be surrounded by water and in the bulk of an aerosol particle. And how this relates specifically to the water uptake of particles. So this is the Kohler equation here. So it's the product of the water activity and then this exponential term, which captures like a curvature surface effect. So enrichment of species at the surface will decrease this term sigma here. And enrichment of electrolytes will modify the water activity. So there's like a competing effects basically. But what this does is it modifies the critical supersaturation, which is the global maximum of S, which affects the conditions under which a particle will grow and activate into a cloud droplet. The other interesting thing about aerosol particles being really small is they're really, really hard to measure. So when we want to get the surface tension of an aerosol particle, it's quite common to like make a bulk solution or impact a particle on a plate and then probe it. But it's quite difficult to measure the surface of a particle without actually touching the surface. If you think of like impacting something on a plate, all of a sudden you've gone from a sphere to some sort of like partial sphere, either like a half sphere or less if it's a very hydrophobic plate. But there are a few people who've been doing contactless measurements, so like suspending a particle in something like an electrodynamic balance and then measuring the surface tension that way. So Brian Bishkek is someone who does a lot of that. And these two plots are showing two binary systems using our surface tension prediction, which we use with this equation down here. So we can find the solution surface tension by using the reference state surface tension for each compound, which is this sigma I naught, plus this activity ratio. So this is now your activity in the surface and your activity in the bulk. And then this script A is the partial molar area of species I in the surface. So that's like meters squared per mole. And what we get is these two curves here. So we can actually replicate quite well the binary solution surface tensions for a water ethanol system and a water sodium chloride system. The black curve represents what a surface tension would be if you said that the depth of the surface is approximately that of a single water molecule, so about 0.3 nanometers. And the orange curve is if we said, let's go a little bit more extreme and say it's like 3 water molecules or 1 nanometer. And then this other curve is, the lower curve is, let's go more extreme in the other direction and say it's 0.1 nanometer, so more like a single bond length. Turns out for these two systems that just saying the surface is at depth equivalent to about a water molecule actually leads to pretty good agreement with measured solution surface tensions. Thinking about size effects, so this is kind of a oddly structured figure, but hopefully it makes sense. It was mainly so that C and F would be on top of each other. But panels A, B, and D show the normalized mole fraction in the surface of a water glutaric and sodium chloride particle. So like mole fraction of water in the surface divided by mole fraction in the bulk. For different sized dry diameter particles. The main thing here I want to show you is that basically all the particles that are greater than or equal to 50 nanometers don't really have any difference in terms of either their solution surface tension in panel E or the partitioning of any of the species in panels A, B, and D. But for the 25 nanometer particle, and especially the 10 nanometer particle, we do actually start to see quite a big difference in surface composition. Panel C and F are kind of like conceptual to show you what the composition of the surface and bulk would look like across different relative humidities. Now you may be wondering, like, is this relevant to any other like real world conditions in terms of cloud droplet activation? So this was measurements taken by Chris Rule in 2016, those 4 sort of orangey red points. And those show measured saturations and particle sizes. So the one without a vertical line is what they report as the critical supersaturation for a water superuric acid and ammonium sulfate particle with 150 nanometer dry diameter. And now these two curves here represent old approaches that we used for predicting the surface tension of a droplet. So this is just like a weighted average approach up here on top. And this is assuming the surface tension is that of pure organics at the bottom. And we find that those are kind of like our upper and lower bounds. And if you use a surface with a depth of about 0.15 nanometers, you actually get pretty good agreement with the measurements that Chris Rule reported, which is still kind of a reasonable surface depth. If you start going below that, maybe it's less reasonable. I mean, like mathematically, you could say it's like 0.01 nanometers, but physically, what does that mean? It's like a fraction of an atom at that point. Talking about smaller sizes, because in 2 slides ago, I just said big particles don't have any differences, but now we're looking at a 50 nanometer dry diameter particle for the same composition, and we see much more interesting polar curves here. So what's happening with these 2 peaks on all of these is there's like a very rapid change in particle surface tension with respect to the diameter of the particle. And so the first peak roughly corresponds to the polar curve if you assume the surface tension of water, and then you get this transition. And then this is the polar curve of like approximately pure organic. There's a little bit of variation here because it's not entirely pure organic, but that's what's driving this sort of unique like double peak behavior here. How this looks in terms of like relevance to cloud conditions. So this is showing some different reported maximum supersaturations for different cloud types. So polluted clouds, background clouds, continental clouds, and marine clouds. The circle and the square were those two old approaches, which I just said were the bounding ones, and the Butler equation was the new, more thermodynamically rigorous approach. So we can see that, like, for a lot of particles, if you use that old like lower bound limit, there's not a huge difference. But as you get to smaller particles, there starts to be more variation between the more thermodynamically rigorous approach and the two simplified approaches from the past. So like it doesn't look like a ton in terms of the difference to the critical supersaturation, but when you think about the number of aerosol particles in a rising parcel of air, this could have a substantial impact on the cloud droplet number concentration. It's also important to note that there also can be partitioning of organic species to and from the gas phase. So previously, all those systems I showed were basically non-volatile organic compounds, right? So they're fully in the particle phase. They don't really appreciably partition to the gas phase, but something like isoprene can. So isoprene can have pretty substantial gas particle partitioning, and we find that just including like a curvature effect with the co-condensation of isoprene is has a pretty substantial effect as well. So you really can't neglect that either. So the red dots are if you assume that the dry composition of the particle is fixed and there's no moving back and forth to the gas phase. And the black markers assume that the gas phase can have isoprene partition back into it. So this is like a much more substantial decrease in the critical supersaturation. So isoprene is more realistic too in terms of atmospheric relevance than sulfuric acid. So this also could have important implications for cloud droplet number concentration. All right. Now I know what you're thinking. He was talking about phase separation before, and that hasn't shown up yet. Well, it does now. So thinking about these like simplified models where we have a single bulk phase and a three-dimensional interfacial region, particles can phase separate, right? So now we also have an interface between your two liquid phases in the particle, and you have this three-dimensional surface phase too. So we treat liquid-liquid interfaces as like a two-dimensional dividing surface, and we say that any sort of partitioning to the interface is actually accounted for between the liquid-liquid partitioning, which would imply that there's also a liquid-liquid interface between the three-dimensional surface and the bulk phase. So now we have this sigma alpha beta between phase alpha and phase beta. And then we have sigma S on top of the bulks, on top of the surface. And then at the bulk surface interface, we have sigma LS. Sigma BS was maybe not the best choice of name there, so we went with LS. Well, it moved ahead there. Okay. So we used a couple different models for interfacial tension. So these were 4 different approaches plus a control, no IIP. So the simplest is Antonov's rule, which is this like very ancient method of predicting interfacial tension. Well, not ancient, but 114 years old or something like that, 117, which just says that it's the difference between the surface tensions of phase alpha and phase beta. About 50 years after that, there was a semi-empirical model developed here, which includes this fit parameter phi. And you can actually rearrange this equation under, you can solve for phi in such a way that this equation, the good Girafalco good equation, reduces to Antonov's rule. Then we developed a third approach called the weighted mean, where we attempted to try and find a like virtual composition for what this two-dimensional phase boundary would look like. So this has a single variable eta here that we have to solve for to give a virtual composition of the interface. And then this last one, the geometric mean activity coefficients, this is actually a rearranged form of the surface tension equation that I mentioned a few slides ago, with the assumption that the pure component surface tensions are equal to 0. Because if you had like a pure water solution and you had 2 layers of it, what's the interfacial tension between 2 layers of water? We say it's 0. So you can rearrange that and have a single variable to solve for, which is actually just the interfacial tension between 2 liquid phases here. So I talked about also how surface tension is difficult to measure. Turns out interfacial tension is even more difficult to measure. So there's very few measurements of the interfacial tension in aerosol systems. So this was actually a bulk measurement taken by Mi-Jung Song in 2013, I believe, for a water, polyethylene glycol and ammonium sulfate system right near the onset of liquid-liquid phase separation. So in this case, we see that the geometric mean activity coefficients equation does the best at replicating the interfacial tension. This is a log scale on the y-axis, so it looks fairly different, but it's actually better than any of the others. And then these more extreme cases like Antonov's rule and the weighted mean do very poorly for replicating the interfacial tension in this case. And then we decided to look at some other systems, and turns out that things are a little more complicated, as they often are. So if you have much more immiscible systems, so in this case, water, dodecane, and potassium chloride, and water, benzene, and methanol, more extreme treatments of interfacial tension actually replicate the interfacial tension that was measured much better. So most of the measurements for interfacial tension actually come out of the oil and gas industry. So there's much more of these like extreme systems and very few of these like partially miscible systems. But for like this brine system here, where there's basically no dodecane in the aqueous phase and no water and potassium chloride in the organic phase, the best is Antonov's rule. And then for the benzene methanol system, which is like kind of an intermediate miscibility system, although still pretty extreme, we see that the weighted mean approach generally does the best at high concentrations of methanol, so closer to phase separation, and then far from phase separation, where it's basically just completely separated water and benzene. Antonov's rule performs much better, well, relatively speaking, in terms of replicating the interfacial tension. Now I'm going to switch a little bit and talk about sigma LS here. So the interesting thing is, if you include this second interfacial tension term, it's having competing effects with the interfacial tension between the aqueous and organic phase. So if we think about how these interfacial tensions are modeled, they're basically driven by compositional differences. So near the onset of liquid-liquid phase separation, but you're still a homogeneously mixed particle, we would expect sigma LS to be quite high, which we can see in some of these models here, like panel A, because what's happening is you're having a lot of organic species enriched at the surface, and then a very strong concentration gradient into the bulk phase, right? So that would encourage the particle to phase separate because it wants to reduce that difference in concentrations, which would lead to the development of sigma alpha beta. But now there's big concentration gradient between alpha and beta. So sigma alpha beta wants to be minimized, which feeds back. And so there's this sort of complex interplay between the two. And just to show you kind of an idea of what the magnitude of these can look like, these are the four, the three sigma S, sigma LS, and sigma alpha beta. The other thing to note is, like, when you talk about measuring surface tension in something like a Langmuir trough, if you expand the surface of a system, you're expanding the area both of the liquid surface interface, so sigma LS is having an effect, and the gas surface interface, so that's sigma S as well. So we can say that sigma S star is actually the value that we solve for in the Butler equation, so that equation about like 10 or 15 slides ago, where I talked about the ratio of the activities. If you subtract sigma LS from that, you get the top contribution, which is just the boundary at the gas liquid interface. You treat that as a two-dimensional phase. Now, depending on how you actually treat the interfacial tension, maybe these peaks are bigger and maybe they're smaller in terms of relative contributions of things. So like in Antonov's rule, we can see that sigma LS would actually be quite high near the onset of phase separation. However, for some of the others, it's basically a negligible difference, and that it's primarily that like area at the boundary between the gas and liquid that contributes primarily to what you would measure or observe as surface tension. So how does this actually interact with phase separation? Because now I've been implying that there's like some feedbacks. So Paul Ono, who's at Auburn University, he's been taking some measurements of size-dependent phase separation in different aerosol particles. So if we say that sigma ls is feeding back on the particle composition, you get these size-dependent phase separation behavior here. So this is the relative humidity at which a particle will go from being an aqueous phase to an aqueous and an organic phase. And then these are Paul's measurements here, which he used fluorescence for. So he would like dye it with a fluorescent dye, and then when the concentration was high enough, it would show up in its measurements. But we see if you assume sigma ls is not negligible, then basically the only system that really does a good job of replicating the size-dependent phase separation behavior is Antonov's rule, which is kind of unfortunate because it's the one in terms of interfacial tension that maybe does the most poorly. So it was a little bit like, what's going on here? If you say sigma ls is 0, though, you get much stronger size-dependent phase separation for various models. So this is the Girafalco-Good equation, the weighted mean approach, and this is Antonov's rule. They all exhibit really strong size-dependent phase separation here. And then you get, for the ones where interfacial tension is really weak, you basically actually get increasing size-dependent phase separation because like the Kelvin effect scales the relative humidity and increases it there. What values would actually be required to suppress interfacial tension? So for some systems, this is maybe more reasonable. Some treatments of interfacial tension, and others it may give unrealistic values. So like we see here on this first system, so these are the different treatments of interfacial tension in A, B, C, and D. So this is Antonov's rule. This is the Girafalco-Good equation, the weighted mean, and this is the geometric mean activity coefficient. So again, they feed back on the composition, but the values that would be necessary to suppress liquid-liquid phase separation are only really physically realistic here for these very small particles. So like, and only at like high relative humidities. For this Girafalco-Good one here, maybe across the entire humidity range for the particle, but otherwise, like, you know, is 1500 millijoules per meter squared of reasonable interfacial tension? Probably not. But that's for a very large particle, like 100 nanometers. So we wouldn't really expect size-dependent liquid phase separation there anyways. And lastly, this is some work we've currently been working on. We're hoping to submit this imminently, like next week imminently. But thinking about sort of what's a key parameter in these bulk surface partitioning models, this sigma I naught term shows up quite frequently. So this is the pure component surface tension of a species. For some systems, this is like a really well-constrained variable, right? Like we know the surface tension of water as a function of temperature, like that's been measured hundreds of times. It's like 72. We know it for some organic species, like we know ethanol is between 20 and 25, but we don't really know it super well for a lot of highly functionalized organic species. It's also an open question for what it is for electrolytes. However, there's been a model developed by Carrie Dutcher at the University of Minnesota, which can predict this, but so nothing really for like any sort of atmospherically relevant organic compound that's covered in all kinds of hydroxyl and peroxide groups and things like that. So it shows up in both the solution surface tension equation up here, and then it also shows up in all of the interfacial tension equations down here, except for the Butler equation one, because we set it to 0. So for all of these equations, we're actually using volume fraction weighted averages for the surface tension, because if you were to try and solve for like an equilibrium surface tension of a phase, you would end up with like non-zero interfacial tensions at a homogeneous solution. So the volume fraction, if both of your phases are equivalent in composition, this value would go to 0, which is what we would expect it to be. So we see it showing up in Antonov's rule, in the Girafalco-Good equation, and in the weighted mean approach. So we thought maybe this is a good use for machine learning. So what if we like took what measurements do exist for organic compounds as a function of temperature, And then we fed those into some different machine learning models, and we were trying to predict what the solution surface tension would be. So like if we were to take the SMILES code, which is this string of C's and parentheses and zeros, if we find a way to like maybe numerically encode that as an input into a machine learning model and then get solution surface tensions. So it turns out we can. So we use 3 different approaches to predict solution surface tension. So this first one here is like we're calling this like the simplified approach. And this is actually just using basically elemental ratios and molar mass as inputs. So O to C, H to C, N to C, the halogen to carbon ratios, phosphorus and sulfur were the compounds in the data set. And this actually does fairly well. You can see how well it falls on the R squared, or sorry, on the 1-to-1 line. It has an R squared value of about 0.9. So pretty decent, especially given just the limited number of inputs and the complexity of some molecules in the atmosphere. And then we moved on to some more complex descriptors. So this red plot in the center here uses max keys, which are molecular access keys. So this is like 166 molecular structures that can be represented from a SMILES code. And so we used those for inputs. That performed better, so that gave about 0.97 for its R squared value. And then this final one here are Morgan fingerprints, which is where you encode numerically each atom in a molecule and then everything that's 1 bond away and everything that's 2 bonds away. So it's a little bit more abstract relative to the other 2, but that was the best performing model. And that gave an R squared value of about 0.975. However, it's like way more complex. So the max keys is 166 inputs plus temperature. The Morgan fingerprints are like 2000 inputs plus temperature. So we've been recommending the max keys as like the balance of simplicity and results effectively. These other 2 plots here are 2 empirical fits for predicting surface tension of organic compounds. That usually people use critical parameters to predict these, so like critical pressure, critical temperature, reduced pressure, reduced boiling point, things like that. And we see that they perform really badly when you give them data that wasn't the data they were trained on. You see like the blue here, it's like way, way, way off. And likewise for the green up here. So in general, these machine learning techniques are performing better than any past techniques to predict pure component surface tension. In terms of what the features are that are the most important, so I'll start with the simplified ones because I think those are the easiest to describe. So molar mass is the most important in the simplified inputs. And then H to C, O to C, and N to C, and temperature are also really important for predicting the surface tension of a pure compound. The other elemental ratios were like less well represented in the training data. So like your phosphorus to carbon ratio, we didn't have a ton of training data to work with there, but those are less relevant. So if you wanted to make an even simpler model, maybe just neglecting the chlorines and sulfurs or treating them as something like an oxygen or a hydrogen could be a good option. For the max keys, these are a little bit more abstract. So the max keys, the most important feature was temperature. And then they use these sort of like alphanumeric encoding things for different atoms. So A is like any atom. So it's like a nitrogen bonded to any atom bonded to an oxygen. So we can see that there's lots of like sort of like larger structural ones here. The presence of nitrogen is quite important in this model when you consider all the max keys that include nitrogen. And then these exclamation points and dollar signs. The exclamation point is like a non-ring bond and the dollar sign is a ring bond. So this would be like 2 compounds in a ring with 2 compounds sticking out of it, basically. And then QQ is like aromaticity. So that's also important, but maybe less relevant compared to something like the NaO. And then lastly, looking at the Morgan fingerprints, we were actually able to go back and extract the SMILES from these, which is a fair amount of work. But we can see for these ones that actually the presence of fluorine was quite important in this model, and temperature is not very important at all. But keep in mind that there's like a great deal more input. So like the contribution to the explained variance in the model is low for all of these. And we see that oxygen is the other atom that's quite important for the Morgan fingerprints. The great thing about some new developments in machine learning is that some models you can actually enforce monotonic relationships between variables. So we used XGBoost. And the nice thing about XGBoost is you can just say like input number 1 is temperature, and it has a like decreasing relationship with surface tension, and the model has to follow that. So it won't give a perfectly smooth curve, but it will enforce monotonicity. So we decided to look at some 2 tracer compounds here that are like atmospherically relevant. So humic acid and fulvic acid. So maybe something you would find in like biomass burning aerosol. And then these 2 points on each are measurements taken at like high concentrations, because there's no measurement of pure fulvic acid or humic acid. And we can see that the models do give some variation in terms of what the temperature dependent surface tension is, like on the order of up to like 10-ish millijoules per meter squared. And then maybe what does this look like for like atmospherically relevant systems as well? So now looking at an isoprene surrogate system. So there's a model called the master chemical mechanism, which can give you all the like photooxidation products of isoprene. We took those SMILES codes and ran the surface tension models for them. And then we also made the assumption that everything has the surface tension of water, which is the blue curve. Water is always blue. And everything has the surface tension of 35 for the organics, which is the green curve, because organics are always green. And we get more variation for this isoprene system in terms of the effective solution surface tension, because there's a lot of variation in the predicted surface tension. And we can see that just basically using any treatment of pure component surface tension that's not that of water affects the critical supersaturation on the Kohler curve here. And then there's like less intra-model variation. Looking at alpha pinene, so we ran the same degradation scheme for alpha pinene and got the products from that and ran that for the surface tension models for that. And we actually see this interesting behavior where it feeds back on the gas particle partitioning and changes the diameter at which the particle activates into a cloud droplet. But in terms of its effect on the solution surface tension, there really isn't a big one. What's happening here where it increases is like highly non-ideal mixing. So like a lot of partitioning of stuff into the surface phase. It actually can lead to slight increases in the solution surface tension, like slightly higher than water. That's something we found in the first paper, to get these like very slight increases. And then you'll get phase separation and it'll go back down, like right around here. But that is to say, basically for the alpha pinene system, the selection of model basically had no effect on the solution surface tension or cloud activation conditions, as long as you use the assumption that it's not water. So for some systems, this might be more important, but these were the 2 that we tested. So there's more work to be done here, I think. So lastly, my conclusions. So bulk surface partitioning can replicate measured surface tensions and critical supersaturations in aerosol particles. The inclusion of interfacial tension with bulk surface partitioning leads to size-dependent phase separation in small particles in agreement with experimental measurements. And machine learning techniques can reproduce individual surface tensions to reduce model assumptions. But some things like more functionalized compounds are lacking in training data, as well as compounds with more heterogeneous functional groups like phosphorus and halogens as well. With that, I have a few minutes for questions. Does anyone?
Brian, there's more questions.
Yeah, thanks for this deep dive into surface tension, interfacial tensions, which are really crucial to get the Kohler curve and cloud activation, water uptake right. And indeed, we don't really know how they scale with temperature, etc. in this aqueous solution. I was wondering, I mean, there's still what I remember in that community is a big debate if at activation you just use the surface tension of pure water in the Köhler curve or not. And you hinted to the rural paper, but I think Facchini or Dowd, some of the leading figures, maybe you and this group was also involved in that, show that if the surface tension changes during water uptake, Köhler curve looks completely different.
Yeah.
And now we know how complex these particles are. Every particle has organics in principle. There's not really pure inorganic particles anymore. Does that mean all our cloud models or cloud activations are off? You know, I mean, is the next step to put this all into, you know, Reuter et al., I think from Mainz, they had a really nice Köhler curve cloud regime sensitivity study, depending on these parameters. How wrong are we, you know, in terms of making clouds in the models by neglecting them?
Yeah. I mean, so I'll address your first question, which is like, should we put this in like a cloud parcel model? If you include phase separation, these calculations are extremely slow. Like it can take days to run a particle. So maybe that speaks to my ability to write code elegantly, but so we at the moment would need some sort of more simplified approach, like some sort of sigmoidal fit or something, to account for surface tension. Yeah, I mean, I think like we know that the surface tension of these things is not equal to water under a lot of conditions. And the other important thing is that, like, as you mentioned, it does affect how things, like how it affects like the organic uptake and stuff. So it's not necessarily just the polar curve peaks, but it's also like the size of the particles as they grow, which, and then there's like a feedback loop on that, right? Because it affects the curvature and so on.
Very challenging.
Other questions?
A great talk. I have a question about the machine learning part. So you mentioned that like when you try to derive this temperature dependency, like you use this or you force XGBoost to take this monotonicity. I was just curious if you don't do that, like you just let the model train without constraint, you have something similar or they behave.
So you get like a generally decreasing trend here, but it's not it's possible that you would get it like generally going down, but every now and then it'll pick one point that it will say like it actually increased with temperature. And that's a function of the fact that when we trained it, we split up, like we randomized everything, so it didn't receive all the temperature points in sequence. So one thing we've discussed is like, and I'm not entirely sure this is a good idea, but like you could run the models for an individual compound across a bunch of different temperatures and then maybe like fit a curve to it as a function of temperature dependence. And then that would give you like an even smoother surface tension dependent curve. But now you're fitting a model to a model, which is, I think, has a lot of, you know, ethical considerations, I guess, for lack of a better word, in terms of like, is this a valid assumption to make? But basically, like, because the way the models are trained, they wouldn't always receive like the temperature, like it would receive like maybe one humic acid and then like an ethanol at two different temperatures, and then it would update the model weight. So it's not like it received all the humic acids with temperature at the same time. And I'm not entirely sure how you train a model like to select the same compound at different temperatures and update the weights that way, because it was like a very large library of measurements that we use. But yeah, so the short answer to your question is like it's generally decreasing, but it looks a lot worse. It's kind of like a stair-step function.
Any other questions? If we don't have any questions, let's give a round of applause.
Thank you for Brian. Thank you for.